So I actually do have a new hike to tell you guys about since we're starting a new chapter. Pull the chat up. This is a picture of another hike we did in the Nashville area. So if you're wondering, I want to get away for spring break, where should I go? You should go to Nashville if you've never been. Anybody been to Nashville before? Nashville, Tennessee, not Nashville, Arkansas. Very different cities. It is such a cool place for so many reasons. Can I jump in the water? If you want to, it's going to be cold. But I saw people last week with all the snow. There's some friends of ours, they have a pool. They did. They jumped in their pool last week in all the snow. They're crazy. I could never do that. After spiders, my number one biggest fear is like ice cold water. Okay. So anyways, this picture is a picture we did right around the Nashville area. There's several hikes we did, and it's called Walls of Jericho, but it was a kind of an all-day thing. So it was about an hour and a half drive to it, and then a 9-mile hike. So pretty, that's not like you're going to finish it in an hour. It's like an all-day commitment. But it was so fun. And here's the deal. You get to this spot right here is like the down and back point. And we stopped and ate our lunch. And then a lot of people would just be like, oh, a pretty little pond, and hike back. But what we did a little research on it, and we found that there was a hidden waterfall. So we're like, we've got to find the hidden waterfall before we go. So what we did, let me grab my pen, is if you hike back this way, I don't know if you can see my arrows, like back over the waterfall. And so there were some stones over here. We kind of crossed over here, and then we just hiked back in here. So the next picture you see is the view hiking up in there, turning around, looking down on top of the waterfall. And then if you keep going a little bit more, there was a hidden waterfall. It was so cool, guys. It was seriously, this waterfall is a lot bigger than it looks. But what's cool about it is it literally just travels like through, it goes through all of this rock. And so like all this water is coming out from some rock, and it was just really, really cool. But that was another fun hike. So if you go to Tennessee, if you go to Nashville area, there's a lot of good hiking to do around. But okay, enough about hiking. Chemical reactions. So this is chapter 5 officially in the textbook, and I will continue to remind you and continue to harp that reading the textbook, I think, is essential and critical and important for this course. Remember, I assign a few chapters, not chapters, a few sections with every lecture. And so please take the time to at least skim over them and flip through those pages and glean through that material. I'm not asking you to spend 2 hours reading every day. I think you would all benefit from it. So these are the first few sections of chapter 5, and the goals that we're going to hit for today. We're going to learn how to write chemical reactions. We're going to learn how to balance them, and then we're going to spend some time classifying them. And when we get here, a lot of different pieces of information from previous chapters are all going to compile together. So it's going to feel like a lot. It's all stuff you know how to do. It's some stuff you had to do for exam 1, writing ionic compounds and the names and the formulas. But a lot of it's going to come together into one big thing. So be patient with yourself when you get to number 3. But when we talk about chemical reactions, my favorite way to introduce this is talking about food, because why not? Food, anytime I can talk about food, I'm just going to. Who likes to cook? Anybody like to cook? Cooking is way cheaper, right, than eating out all the time. I promise it is. It takes more time to go grocery shopping, I know. But if you cook, you're going to save money. And all you need to be a good cook is a good recipe, okay? You don't have to like be Chef Boyardee. You just need a good recipe. Thank you, Joanna Gaines, for sharing all your good recipes with us, okay? But here's what a good recipe includes. It includes these things: how much of each ingredient, what to do to the ingredients, and then it should tell you about how much of the final product, how much food you're going to make. And this is especially important if you're cooking for people, right? I'm a huge fan of leftovers. I don't want to cook every single night. I do like to cook, but I don't want to cook every night. So I usually double a recipe, okay? But it's important to know that. And that's what a chemical reaction is also going to tell us, a good one. It's going to tell us how much of each reactant we're going to have, and how much Gordon Ramsay wishes he could cook like me. Well, I need to come to your house then, okay? All right. So anyways, how much of the final product we get. So that's what a good chemical reaction will tell. So I would literally want us to, as an example, write down the recipe for a s'more. Okay. I know winter's almost over. RIP, good campfires and s'mores for a little while. Gordon Ramsay wishes he could cook. He can. So let's write down the recipe for s'more. What ingredients do you guys put on a s'more? Y'all tell me. Water on your s'more? No, I don't put water on a s'more. Okay. Marshmallows. Okay, marshmallows. Plus, what else? Graham cracker. I'm going to abbreviate. Chocolate, that's right. And if you really want to do it the right way, I promise, trust me on this, you'll put some mayonnaise on it. Okay? I'm kidding. I saw all of y'all writing and y'all looked up like, just kidding. I didn't even do that when I was pregnant. And I didn't eat weird things when I was pregnant. I promise you though, you will hear people say they eat weird things when they are pregnant. There are real things such as mineral deficiencies and people, there's some weird stuff, but I didn't do any of that. Okay. I'm kidding. But then that's what you get. You get one s'more. All right. So we need to be more specific though. Yeah, we don't do water. Peanut butter on a s'more, I would not say no to that. Okay. We need to be more specific. How many marshmallows? How many grams? This is probably where the recipes are going to vary per person. All right. But a typical s'more, let's be honest, one marshmallow. I'm a 2 marshmallow kind of person. 2 graham crackers, and then let's say half a bar of chocolate. Is that doable? Is that agreeable? Yeah, I'm a 2 marshmallow kind of person for sure. All right, so this is how specific it can be. And then you might even add the fact that you probably want to add some heat. Okay, nobody wants to eat that's going to make it better and melty and good. And this is exactly what a chemical reaction is going to tell us. It's going to tell us how much of each ingredient, what we do in the final product. So let's look at a real example. Carbonic acid, I'm going to read this sentence. Carbonic acid in low pH environments breaks down into bicarbonate ion and hydrogen ion. Carbonic acid and low. So we got carbonic acid right here. We read chemical reactions, by the way, from left to right, just like you're reading a sentence. In low pH environments, breaks down into you guys should know what bicarb is. It's actually right here. HCO3 minus, that's a polyatomic. And then the hydrogen ion. Okay, now this is actually a really, really important chemical reaction. Why is it important? You may can guess from the picture I included. This is important for maintaining what? Anybody know what bicarb is useful for in our bodies? Maintaining, yeah, thank you, Keegan, blood pH, okay? Anybody know what physiological pH is? It's a range. Your body has to keep it really accurate, but it's a small range. Anybody know? Okay, Matt, Chris, 7.35 to 7.45, that's right. That's exactly right. So physiological pH, your blood pH should be maintained between 7.35 to 7.45. If you know anything about pH, we're going to talk a whole lot about pH when we get to chapter 10. But if you know anything about it, pH 7 is neutral. Okay, so this is pretty close to neutral, slightly alkaline, slightly basic. But your body, I mean, if your blood pH falls too low, you'll go into a coma. So bicarb is really, really important from a health standpoint. Okay, let's label the different parts of the reaction. Obviously, the first arrow over here pointing to our carbonic acid, this is the reactant. So the reactants are substances that are going to undergo the chemical change. That's what's changing. And it can change so many different ways. They can break down, they can combine together, they can rearrange. We're going to look at those later on. And then the other part on the right are the products. Okay, products. And these are the substances that are formed in a chemical reaction, right? These are the things you're going to make. So that's the basics. And then you put an arrow between those from reactants to products. So you always write reactants on the left, you always write products on the right, and you draw an arrow from left to right. Another thing to know is that when this kind of hits on, if you remember Dalton's atomic theory, we said that atoms are just recycled endlessly through chemical reactions. We don't create or destroy new atoms. And that's just what I want to remind you of here. Okay, bonds, whether they're ionic bonds or covalent, when a chemical reaction happens, the bonds are broken and then the atoms rearrange and they form new bonds. Okay, so the bonds are rearranged. essentially, in chemical reactions to make new compounds, but atoms are not created or destroyed. And this is actually a law in science, and you guys may have heard of it in a previous chemistry class or high school chemistry class, the law of conservation of mass, okay? Mass is always conserved across chemical reactions. We don't get rid of it, and we don't make more stuff or more of it. So remember those things. And that's going to be, this is kind of the foundation for why we have to balance chemical reactions and why on paper they have to be balanced. All right, chemical reactions often also include the physical state of the reactants and the products. So what you see down here, and you'll see this a lot in your textbook, you don't always see it, but often you will see little things abbreviated after the formulas. And what do those stand for? Those letting you know if something is a solid, a liquid, or a gas. Okay, so there's actually 4 abbreviations. Obviously 3 we can think of right off the bat. Solid is abbreviated with an S. Liquid is abbreviated with an L. Gas, abbreviated with a G. And then there's one more. Can anybody guess what I'm going to write? Okay, Jonathan said it. Aqueous. And you abbreviate that AQ. Okay, now what in the world does aqueous mean? Is that a fourth state of matter? No, it's not a fourth state of matter. But why do we denote it separately from solid, liquids, or gases? Anybody know what aqueous means? Like, what should I think of when I see something that is aqueous? Aqueous just stands for things that are dissolved. Okay, so for example, so it's a in solution, dissolved in solution. So let's look at an example of that before we move on. Let's take sodium chloride. Sodium chloride is salt, right? And you can pour salt in your hand. It's white. It's a solid. And there's small particles. And the moment you take salt and you dump it into some warm water or whatever and you stir it, what's going to happen? We know that salt is going to dissolve. So we could draw this in a chemical reaction. NaCl, solid. That's the type we can pour into our hand or on our food. When we add it to water, oops, what am I trying to write? H2O. It's going to become NaCl, aqueous. Okay, and what's actually happening is it's dissolving. I'm going to zoom in here into its ions, plus and Cl minus. Okay, so when we write aqueous, what we actually mean is that it's broken apart into its ions. We still have sodium chloride overall, it's just dissolved. Okay, so that's what aqueous actually means. So if you see something with that, it's likely an ionic compound. Okay, now covalent compounds can dissolve too. Let's think about sucrose or glucose. Glucose, sucrose, these types of things, these are covalently bonded compounds. It's a lot of carbon, hydrogen, and oxygen bonded together. And if you have, remember the old-fashioned sugar cubes? Anybody seen a sugar cube before? It's a lot of sucrose put together, small particles all, packed together into a sugar cube. Well, you could equally put that sugar cube into some hot coffee or hot tea or whatever, and it's going to dissolve. So you can make it aqueous. That doesn't mean it's breaking apart into ions, okay? But it is a covalently bonded compound that can also dissolve. So it doesn't just have to be ionic. Aqueous can also be related to covalently bonded things. Okay, I mentioned this a second ago, but talking about the fact that bonds are just rearranged. We don't create or destroy new atoms. The law is the law of conservation of mass. Okay, which just says what we've been saying. Mass is neither created or destroyed in chemical reactions, but the implication here, the reason that's important is because this means we have to balance our reactions. And when we balance, we have to have the same number and kind of atoms on the product side as we do the reactant side. Okay, the same number and the same kind of atoms on the product and the reactant side. All right, so now we're going to start looking at some real examples. We're going to start doing some actual balancing. If you're new to balancing chemical reactions, this is going to feel like a lot. If you've seen this before, I hope this is a good review. But let's look at this first one. So we got, and I want you to get comfortable saying the names of compounds too. You've had to do that. You had to write it or write formulas on exam 1. And now I want you to actually practice saying these. So how would you say this? Na we know is sodium. HCO3 is bicarb. So this is sodium bicarbonate. Okay. So sodium bicarbonate is going to decompose or break down into sodium carbonate, water, and carbon dioxide. Right. And looking at this, is it balanced? Do we have the same number and kind of all the atoms on the reactant side as we do the product side? And let's just start with the very first one we see, sodium. Okay. Na, I have 1 sodium atom on my reactant side. And if I look at the product side, the only place I have sodium is in that first compound. If I had it in more compounds, I would have to add it up across all the compounds that it was present in. But it's just in 1 compound. So I see that I have 2 sodium atoms. So I've got 1 on this side, 2 on this side. It's not balanced. So if you're looking at the reaction below down here, the way we balance this, we cannot come in here, like if I'm going to mess with this formula, I cannot come in and just put a 2 right here. Why can I not do that? That messes with the formula. And your formulas are set. You cannot mess with. We have to write correct, accurate formulas, and then we have to balance separately. So I cannot do that. But what I can do is what you see we did down here below. I can put a 2 out front. Okay, and that is going to multiply every single atom, even the hydrogen, carbon, and oxygens, by 2, the number of them by 2. Okay, so knowing that, now let's reassess. Okay, if I put a 2 in front of sodium bicarb, now I have 2 sodium atoms. But how many hydrogen atoms do I now have? Well, I also have 2 hydrogen atoms. I also have 2 carbon atoms. And how many oxygen total do I have now? I see this little subscript 3, and that applies to the number of oxygens in my 1 compound. So yeah, you put a 2 out front, now you got 6 oxygens. So that's not 60, that's 6 oxygens. And then we need to make sure we have the same thing on the product side. Okay, I have 2 sodiums. I have 1 carbon there and 1 carbon here. You got to add it up across all your compounds. So that makes 2 carbons total. That's good, that matches. Hydrogens, I've got 2 just in water, so that's good, 2 and 2. And then oxygens. I have oxygen in all 3 compounds, okay? I have oxygen right here. I have oxygen in water. So I've got 3 plus 1 plus 2 adds up to 6, okay? So now everything's balanced. So you always need to recheck. After you put a number out front, I'm going to explain what that number is. You need to recheck your balance and make sure it's good and it's final. And what do we call these numbers? Anybody know? I almost said the word a second ago. Anybody know what we call these numbers that we're going to put out front to use to balance? Thank you. Yes, I'm seeing it in the chat. Coefficients. These are numbers placed in front of a formula, okay, to balance the equation. And then the final balanced equation, you might hear me say balanced equation or balanced reaction. It's the same thing, balanced equation, balanced reaction. It should have the same number and type of atoms on both sides, okay? So, all right, so now we're actually gonna do some practice. I've got kind of 4 little rules we're going to look at in a second, just the same way we looked at some rules for Lewis structures or molecular geometry. We got some rules that are going to help us. And you don't have to follow these always step by step, but at first, until you get comfortable with it, it is helpful, I think, to follow these rules. But going back to, before we jump into those rules, I want to ask you this question. How would you say the following reaction? So if you're looking at this reaction right down here, how would you actually say these compounds? This is what I want you to get comfortable with. Sure, and I'm not saying K2SO4 plus BaCl2. No, I want you to tell me the name of the compound. Okay, so what is the first one? Anybody want to unmute and say it?
Potassium sulfate.
Yep, okay, so you got to know your polyatomics, number 1. So if you don't know those, this is going to be hard. So SO4 is sulfate. We know K is potassium. And by the way, you might want to grab a periodic table. If you don't have one of those handy, either open up a window on your internet and pull up a periodic table or grab one from your textbook or from your notes somewhere. That's going to be very handy to have these next several the rest of our time in lecture together. So potassium sulfate plus, now we got BaCl2. Anybody else want to name that one? Nobody?
Barium chloride.
Barium chloride, thank you. So potassium sulfate and barium chloride are going to come together, or they're going to react, rearrange, and we're going to get potassium chloride and barium sulfate. So things kind of just switched around. And so now you want to ask, is it balanced? So how should we go about balancing this reaction? Anybody have any suggestions or any thoughts? We're going to use coefficients. Where could we put a coefficient, and what coefficient does it need to be to get this thing balanced? So you got to take an inventory. What I like to do is I like to write down all the different kinds of atoms that I have. So I've got potassium, I'm going to write K, and I'm going to take an inventory. How many Ks do I have on each side? Well, I see on my reactant side, I have 2. On my product side right now, I just have 1. Okay, and you guys are giving me suggestions right now. I'm gonna put those into play in just a second. One thing I want to mention though is I know that I have sulfate on both sides, product and reactant. If you have a polyatomic on both sides, then you do not have to balance the S and the O separately. You don't have to balance sulfur and oxygen separately. You can balance as a unit. So I'm just going to write how many sulfates do I have on each side. I've got 1 and 1 so far. Then I know I also have barium and I also have chloride or chlorine, chloride. Okay, so from the chat, people are suggesting 1 and 2 to put a 2 in front of KCl. Okay, so if we do that, now let's reassess our inventory. Now instead of 1 potassium on the product side, now I have 2. And oh, I actually think I wrote it. This should have been a 1, not a 2. Originally we had 1. Now you put the 2 there. Now we have 2. So now everything is balanced. Okay, so that was a very, very simple one. Just 1 coefficient fixed everything. But I promise it's going to get a lot more complicated than that. Okay. All right, so rule number 1, if you're going to balance chemical reactions, the first thing I want to make, the first thing I want you to worry about, and the first thing I want you to worry about is not, is it balanced? The first thing I want you to worry about is, do I have the correct formulas? Did I write it out correctly? And you won't always be given a sentence like this, but if I did give you a sentence, I want you to be able to read it and write out what formulas you have. And then what's very, very important is if you're going to do this correctly, you have to remember which elements are diatomics. Okay. Anybody remember from, I guess that was the video lecture I did last week during all the snow. We had a slide right here on, you guys remember this slide from the video lecture when we talked about molecular compounds? There's 7 elements that are diatomics. And what's important is that you know to write hydrogen, for example, as H2 and not H. Okay. You have no hope of balancing it correctly if you don't write your formulas correct. And these particular elements have to be written as a diatomic. So, all right, let's write this one. I want you to take a minute and try to write this. Hydrogen sulfate reacts with sodium hydroxide to make sodium sulfate and water. And remember, when you write your compounds, they have to be neutral overall. The rule we learned with ionic compounds when you write them out is the number of positive charges from your cations have to add up with the negative charge from your anions. That all has to add up to 0. So hydrogen sulfate, sodium hydroxide makes sodium sulfate and water. All right, for hydrogen sulfate, you should have H2SO4. How did I know that? How did I do that? Well, I know hydrogen is a +1 cation based on its location of the periodic table. I know sulfate is a -2. I just know that from straight memorization from the polyatomic ions. You can always do the switch trick, remember? To figure out how many cations and anions you need. All right, so that's hydrogen sulfate. Sodium hydroxide. What did y'all get for that? Somebody type it in the chat for me. Sodium hydroxide. Thank you, Summer. NaOH. Okay. Sodium hydroxide. You just need one each. It's a +1 and a -1, cation, anion. So just one each. All right, then sodium sulfate. So we're going to have Na is sodium. Sulfate is SO4. Is this right? NaSO4? I see some people shaking their heads. You need a 2 after the sodium. That's right. We need 2 sodiums because this is a +1 cation and a -2 anion. So just like you needed with hydrogen, we need 2 cations to balance the anion. And then water. Okay. So you see how we're drawing from a lot of things we did in chapter 3 to do this, to even write this? And this is even half the battle. This is not the goal of today. The goal of today is to learn how to balance these things after we write them and then classify them. Okay. So that's number 1. So I want you to make sure you're writing correct formulas before you even ask yourself, is it balanced? Questions on what we just did? Okay. Rule number 2. So it's the same equation down here. Once you get it written correctly, we're going to add up the atoms on each side, and then we're going to start putting coefficients in to balance. And this is, I said this earlier, but I want to renote this. Polyatomic ions can be treated as a single unit if they occur on both sides of the equation, on the reactant side and the product side. So do we have any polyatomics that we can treat as a unit here? Oh, I have a question in the chat that I just saw. Hold on, Haley. I'm going to come back to what you just said. Kishan, why did I write a 2 after sodium right here? Anybody want to pop in and help answer that? If not, I'll fill it. Someone told me to do it. So someone knows why we did it. Sodium is not a diatomic. No. Good guess, but it's not a diatomic. Sodium is a +1 cation. Okay. Sulfate is a -2 anion. So remember the switch trick? We have to write a neutral compound overall, meaning the positives and the negatives have to add up to 0. Right now they do not. Right now we have +1 and we have -2. That does not add up to 0. So we need 2 of these, right? And I can't just put, like, I can't just put a 2 right there, because then that 2 multiplies everything by 2. I don't need 2 sulfates. I just want 2 sodiums. So the 2 right here in my formula will give me 2 sodiums and 1 sulfate. That is going to add up to 0. Neutral compound. Does that answer your question, Kishan?
Yes.
Okay. That's a great question. I bet you weren't the only one that had that question. Okay. Haley, you said yes, that we have a polyatomic we can treat as a unit. Which polyatomic is it in this equation? Sulfate. Yep. So we're going to treat this as a unit. What about hydroxide? Hydroxide's a polyatomic.
But it's not on both sides.
Thank you, Lucy. It's not on both sides. So we got to balance the oxygen and the hydrogen there separately. Okay, but the oxygens in sulfate, we're not going to balance separately. We're just going to keep it as a unit in sulfate. Okay. All right, so now let's do that. I'm going to take an inventory. We got hydrogens, we got sulfates, we got sodium, we got oxygen. Oh, I already wrote hydrogen. There we go. So right now, currently, I have 2 hydrogens and 2 hydrogens. I have 1 sulfate and 1 sulfate. I have 1 sodium on my reactant side, 2 on the product side. And oxygens, remember, I'm only counting the oxygens that are not in sulfate. 1 on the reactant side and 1 on the product side. So any suggestions for how we can put a coefficient in to balance this?
Would you have 3 hydrogens on the left?
Thank you. I miscounted. We have 2 over here. I didn't even look at those. So we should have 3. Good catch. Thank you, Hunter. Okay, so what should we do to fix this? Here's what I see. I see if you're looking at hydrogen first, let's just start with hydrogen. I see an odd number on one side and an even number on the other side. And when you run into situations like this, you need to find a common multiple. Okay, so what is a common multiple of 3 and 2?
6.
6. So how can we make 6 hydrogens on both sides? Well, the easy way on the product side is just put a 3 in front of water. That'll give us 6. There's no way I can put a coefficient right here and get 6 because I have this one lone hydrogen. So I've got to put a coefficient in front of sodium hydroxide and not, for the time being, not in front of hydrogen sulfate. So what coefficient could I put in front of sodium hydroxide to make it even, at least? A 2? Oops, I'm on eraser. If I put a 2 there, I like that because that also helps me out in another atom that we're not talking about right now, but that helps me out with sodium. I bet a lot of you can see that. So I'm going to go ahead and fix this. Now we have 2 sodiums on both sides. Now I have 6 hydrogens on my product side. I still need 6 on my reactant side, but if I recount how many I have, 2, and this 2 applies to the hydrogens 2 more, so now I have 4. Oops. 4 and I have 6. So I'm still not balanced on my hydrogens. So what can we do now? Two in front of H2O. That's a good idea. Put a 2 there, but that messes up our oxygens, doesn't it? So we got to recount our oxygens. We got 2 there, and we got 2 there. Are we balanced? Are we all done? Okay, so maybe we didn't need to go all the way to 6. That worked out because we had hydrogens in 2 different places on our reactant side. So it actually worked out. We didn't have to do the common multiple thing. Okay, any questions on how we got? Sometimes it's kind of trial and error. Like you try one number and you erase it or you try another one. That's just kind of how it goes when you're getting started with these things. All right, rule number 3 and 4 is you always double check that you're balanced. And that's kind of what we're doing. If you choose to do something like this and write it out as you go, that's going to help you double check that you are indeed balanced. And then lastly, number 4, this is important. If you get everything right, but you forget to do this, I won't count off all the points, but I probably will count off a point. Always reduce your coefficients to the lowest whole numbers. So for example, our coefficients right now, what we had up here, and you can see them also down here, there's an understood 1 here. It's okay to omit the 1 and not write it, except for on Blackboard this week for your labs. Please make sure when you're typing in your coefficients for your reactions, that's basically what you're going to be doing. It's fill in the blank style questions. You're going to be typing, balancing them on paper, then typing your coefficients. And please type the 1, okay? Or Blackboard will count you wrong if you don't type anything. But anyways, it's a 1, 2. There's another 1 here. So 1, 2, 1, 2. We actually can't simplify this. It's already simplified because you cannot simplify 1. But if, for example, when you had balanced it, you got 2, 4, 2, 4. Well, guess what? Your reaction would still be balanced because it's the same ratio. It just would not be simplified. I can divide all these coefficients by 2, right? So just make sure you always double check that you're simplified. Okay, questions on these 4 rules, because now we're going to do some practice. Okay, so the four rules we just walked through, 4 steps. I want you to go ahead and try to do that with this one right here. I'm going to give you a minute on your own to do it. One tip though, one thing I would encourage is when you have something by itself, notice that chlorine is by itself. It's not with any other atoms in a compound. Save that for last because you can put a coefficient in front of chlorine without messing up anything else. So balance your carbons and hydrogens first. And when you have something by itself, always save it for last. Okay, I'm going to kind of jump in. Some of you may have some ideas that you have worked out. Anybody have a suggestion on a coefficient to get this thing balanced? Two CL, Summer says. So put a 2 right here in front of CL. Well, we're going to save that for last. Oh, 2HCl. Gleanna suggests 2HCl. Okay, we'll try that. That's going to give me 4 hydrogens on the product side. I was just taking inventory of those. 2 in front of CCl. Okay, yeah, 2 in front of HCl. And then the chlorine, so total, if I put that 2 right there, that gives me 2 chlorines here and 2 more here. So 2 plus 2, I've got 4 total. The product side, which means I need 4 on the reactive side. I've got 2 already as a diatomic molecule. So if I put a 2 right here, that'll give me 4 as well. So I think that solves that one. Okay, so not too bad. And then it is already reduced, right? Because technically if you read the coefficients all the way across, it would be 1, 2, 1, 2. And you can't reduce 1. Okay, questions on this one? Okay, so let's do another practice. And then I think after that, we'll move on to some classifying. All right, y'all go ahead and try this one kind of on your own. Absolutely, Bradley. Do you want to go back and review anything? Okay. All right, so what I encourage you to notice on this one is that you have some polyatomics. Okay, what polyatomics do we have? PO4, which is phosphate. And we have that on both sides. So I want you to treat phosphate as a unit this time when you balance. So PO4, count the number you have on both sides. Any other polyatomics? Hydroxide, right here we have hydroxide, OH. But we don't have it on our product side. We only have it on the reactant side. So we cannot treat hydroxide as a unit. We have to balance the oxygens and the hydrogens in hydroxide separately, but you are not going to separate out the oxygens from phosphate. You keep those together with phosphorus in the unit of phosphate. So it means we also have aluminum, oxygen, and hydrogen. Okay, so if we're looking at this, you're wondering, how do I get started? Just start with aluminum. It's the very first thing. I noticed that I have 1 aluminum on each side. And then how many, remember this 3 outside of hydroxide applies to everything in the parentheses. So that means I have 3 oxygens. But before I write my number of hydrogens, I have to also count the hydrogens in both compounds total. So I got 3 hydrogens in aluminum hydroxide plus 3 hydrogens in hydrogen phosphate. So that's 6 total on my reactant side. Phosphate, I just see that I have 1 phosphate on each side. Now on the product side, we already wrote the number of aluminum. So the only place I have hydrogens and oxygens are in water, and I got 1 oxygen and 2 hydrogens. So this is the inventory we have so far. And now we can start manipulating this to get it balanced with coefficients. 3 waters, 3 waters. Okay, so if I do that, what is that going to do? Let's erase. That's going to change the number of oxygens and hydrogens. That's going to give me 3 and 6. Was it that easy? Okay. I mean, according to my table here, everything is balanced now. So that one wasn't bad. And then of course it's reduced because you got technically a 1, 1, 1, 3. So you cannot reduce 1 any further. All right, questions on what we just did? All right. Now that you're comfortable, let me make it harder. I'm not kidding. It's gonna get harder. Okay. We're gonna talk about 5 kinds of chemical reactions. So these are kind of a preliminary 5, and then next week we're gonna talk about 3 other ways to classify chemical reactions. And I'm gonna warn you, those ways are a little more difficult than these ways, okay? So 5 that you see here: combination, also known as synthesis, decomposition, displacement. Sometimes it's called single displacement, and then double displacement reactions and combustion. So let's look at number 1. What is a combination reaction? Pretty straightforward here. You have 2 things combining. So for example, A plus B makes AB. 2 things combining into 1 thing. You could also have 3 things combining into 2 things, or 3 things. You could have A plus B plus C make ABC, okay? So don't put yourself in a box, but if you just notice you have more things, more reactants, and fewer products, it's because something combined. Okay, so that's what we call a combination reaction. Decomposition is just the opposite of this. So I want you to take that first reaction we wrote and write a decomposition reaction. We wrote A plus B makes AB. The opposite of that would be AB decomposes into A plus B. It's exactly what we saw when we were talking about the blood buffer system. Carbonic acid breaks down, that's another word for decomposes, into bicarbon hydrogen. Or again, you could have A, B, C breaks down into A, B plus C. Okay, it can look a lot of different ways, but if you have more products than you do reactants, something broke down, something decomposed. Okay, displacement or single displacement reactions. What does this look like? Well, you again can have a couple different things, but one way you can have it is AB plus C. So here's what I noticed. So far on the reactant side, I have a compound of some sort, AB, indicating there's more than one element involved, plus C, which is just a lone element. C, the lone element, will displace something in A or B. All right. It's either going to displace A or B. So how do we know what part is it going to take? Is it going to replace A or is it going to replace B? Well, it depends. If C is a metal, if it's a lone element that's a metal, and this is an ionic compound, right here, what do metals form? Do they form cations or anions when they become an ion? Metals form, thank you, in the chat. That's right, cations. So if it's a metal that's by itself, the metal will replace the cations. So what that looks like is A is the cation, right? Because we always write cations first. B is the anion. We always write anion second. That was part of the rules from chapter 3 when we write ionic compounds. So we'll end up with BC plus A. All right, well, what if C is not a metal? If C is not a metal, if it's a non-metal, I'm going to rewrite my reaction over here. A, B plus C. And this time C is a non-metal. These displace anions. Okay, A is the cation, B is the anion. So what products would we get? This time C is going to displace the anion. So we would get A, C plus B. Does that make sense? All right. So the key indicator here is that you have, on single displacement, you've got one compound in D plus one element. Okay? A compound and an element are your reactants. Double displacement is when you have two ionic compounds. So that would look like this. A, B plus C, D. Actually, I'm going to color code this. If you don't have different colors, don't worry about it. But just for visual sake, I'm going to do cations in blue. A, B plus C, D. Okay, so your cations are in blue here. Anions are in red. And when these rearrange, my Siri just turned on. When these rearrange, what's the only possible outcome? You need to rearrange cations and anions. Ca and Bd. Okay, no. You should put a cation from the first thing with the anion from the second thing. Okay, so if this is, I'm going to write the charges in over the top. Plus, minus, plus, minus. Remember, opposites attract. So we have to take the cation from the first thing, A, pair it with the anion from the second thing. So I see several people did write it. A, D, you got to have a red and a blue in each one. You can't put the blues together and the reds together. And then that leaves us with plus C, you got to write cation first. C, no worries, Kishan. CB. There we go. AD and CB. All right, that's the only way they can rearrange. So a key indicator that you have a double displacement reaction is if you have two ionic compounds on your reactant side. Okay, combustion reactions, to me, I think they're the easiest. They're my favorite because they give you the same products every single time. So the combustion reactions, you start out with a carbohydrate, meaning an element or a compound that just has carbon and hydrogen. And you don't necessarily know how many. Carbohydrates can be wildly different. C5H10, C4H12, it's all different kinds, okay? But it's just carbon and hydrogen in the compound. And then you have oxygen. Oxygen's a diatomic. So you're always going to have some sort of carbohydrate reacting with oxygen. And you always get the same products. Anybody know the products of a combustion reaction? Very simple things we deal with every day. H2O is one of them. Hold on, I'm reading. In high school, Haley said, my teacher compared all the situation, the aspect of marriage, divorce, remarrying. It helped me remember easier. Hey, that's an idea. We could go through and do that. Sorry, let me finish the combustion reaction really quick. You have water and CO2. Okay. Those are the products of a combustion reaction. So, Haley, tell me if I get this right or wrong. Combination, you're getting married. Okay. Decomposition, you're getting divorced. Displacement, how do you describe that one? Marriage, divorce, third person remarrying. Okay. I would say cheating. That's a cheating situation. Thank you, Kiana. Okay, somebody else thought. Somebody getting cheated on. 4, next are both remarrying, both people remarrying. And then 5, everything just crashed and burned and went down in flames. The marriage exploded. Okay. Is that good? All right. Traded partners. Okay, we could get crazy here. Let's not. All right. I hope that helps. That was a really creative thought. Thanks for sharing that. Okay, so now we're actually going to put this into practice. Below, we have your reactants, and they're typed out. So you gotta have to write the formulas, and I want you to practice writing the formulas. After you write the formulas for everything, it might be an element, it might be a compound. You need to consider if you have any diatomic elements and write those correctly. Then I want you to say, okay, based on what reactants I have, what's going to happen? Are things going to get married, or divorced, or are they going to explode? Okay. And then you write your products. And then after you do all of that correctly, then I want you to worry about balancing. Okay. So let's do the first one together. Magnesium and chlorine. Magnesium and chlorine. How are we going to write this? You need a periodic table. I mentioned that earlier, but if you didn't go get one, you definitely need to go get one now. Okay, well, it's magnesium and chlorine. So these are separate right now. You guys are writing the products, or trying to. Okay, so we got magnesium, just Mg, good old Mg, just by itself as an element. Plus you have chlorine. If I had them together, I would write magnesium chloride. So just Cl. And what do I know about Cl? Do I just write Cl and I'm done? Thank you, Kishan. Cl2, it's a diatomic. So here's what I noticed. I have 2 single elements, 2 single people here. What can happen? Well, divorce can't happen because they're not even married yet. So what can happen? Combination, that's what can happen. Magnesium proposed to chlorine. Chlorine said yes. So what are we going to make? What's the formula for magnesium chloride? You have to ask yourself, what's the charges on my cation and anion? Well, magnesium is a +2. It's main group 2. Okay, if you're like, how did she know that? This is all chapter 2 stuff when we sorted out the periodic table. Okay, and then chlorine as an anion is going to form a -1. So you can always do the switch trick, right? What you should write is MgCl2. Now, it's not always as simple because it looks like I just scooted them together. We already had chlorine written as a diatomic. It's not always that simple, okay? So don't think you just shove them together and write it as is. You got to always check the charges. All right, so this was combination. Is it balanced? That's what you check last, and it is balanced. This one, we didn't have to put any coefficients, but again, this is a relatively easier one. All right, next one, iron 3. Any questions on that one, by the way, combination, before we move on? The next one is iron 3 bromide. So we got a transition metal cation. The charge on it is what? What's the charge on iron 3 bromide, or iron? That's right. We look at the Roman numerals and that tells us the charge. This 3 right here means it's Fe plus 3. Bromine is Br minus as an ion. So we got to write a formula for iron 3 bromide, and that formula has to be neutral overall. So you do the switch trick. We're gonna need 1 iron cation, Fe, and then Br3. Now, hydrogen sulfate, we actually wrote that one earlier when we were practicing writing out a reaction in sentence form. We wrote H2SO4. Okay, how did I know that? Well, sulfate is the polyatomic SO4 minus 2. And if you haven't memorized those, then you're going to be way lost on this stuff. Hydrogen we know is a +1 cation. So you ask yourself, how many cations and how many anions do I need to get the neutral compound overall? And you write that. Now, what can happen here? What kind of reaction is this going to be? What do I have? I don't have two elements. I don't have an element and a compound. I see two ionic compounds. Double displacement or switching partners, however you want to say it, whatever helps you. So you got to take the cation from your first compound, and that's going to pair up with the anion from your second compound. So I'm going to box those in green. Cation, remember those are always written first, is going to pair up with the anion. Wasn't there a TV show where two people married switch wives? Yeah, Wife Swap. Is that what it was called? Those shows always went badly. That's a terrible idea. Celebrity Wife Swap was awesome. Oh gosh. Reality TV. I don't even know what the good reality TV shows are anymore. I had a lot of friends watch the Kardashians, but I never got into that. Yeah, that sounds crazy is what it sounds. Okay, so hopefully you've attempted to write out your compounds now. Let me see if I can do it. So we should have F. Tell me if I get it right. FeSO4. Is that right? Plus H2Br3. Is that right? To just take what we did and write them over there like that? I'm seeing a lot of y'all shake your heads no. No, we can't just swap it. We got to really assess the charges here. Okay, so iron is a +3, sulfate is a -2, right? That's what we wrote over here. So we can't just write it like I just did. I'm going to erase this. How many irons and how many sulfates do we need? You got to do the switch trick. We're going to need 2 Fe2. Sulfate, we're going to need 3 of these, right? If you do the switch trick. So you got to put, thank you, Haley, you got to put the parentheses around it when it's a polyatomic and you need more than one. And then for hydrogen bromide, it's a +1 and a -1. This one's actually very simple. You write HBr. Okay, +1, -1. You just need one cation and one anion to get your neutral compound overall. Okay, now that you have correct formulas, now you can worry about balancing. So I'm actually going to go in here and erase these boxes because that's going to get as annoying to me when I'm trying to balance.
I have a question.
Yes.
Why do you put the 2 in front of the hydrogen on the reactant, but not the product?
Like this 2 right here, is that Keegan talking?
Yeah.
Okay, H2, but there's no H2 over here?
Yeah.
That's because I'm trying to write a balanced compound between hydrogen and sulfur, or sulfate. So I have an H +1 and I have an SO4 -2. So if I'm just looking at the charges, Keegan, I have +1 and -2. That does not add up to 0. So what I did is I said, I need to double my +1 charge here. I need +2. +2 and -2 add up to 0. And I do that if I have 2 cations, right? So I wrote 2 cations into my formula, and you do that with subscripts. Okay, but when I'm over here with hydrogen bromine or bromide is a different cation or anion. Bromide is a -1 anion. Hydrogen's already a +1. So +1 and -1 already add up to 0. So I just need one each in my formula. Does that make sense?
Yeah, but I thought you said like if it's a diatomic, you put the 2 on it.
If the element's written by itself. You see up here, chlorine was by itself. In a formula, you don't always write it as a diatomic. In a formula, you write it to add up to 0.
Okay.
That's a great question. I'm glad you brought that up because other people might have had the same question. Diatomics only apply when you are writing the element as an element by itself, not in a compound? Yes, Haley wrote that in the chat as well. Ask that question. Okay, so now we can balance. So I notice I have iron. I've got 1 iron on the reactant side. I've got 2 on the product side. So I'm just going to guess that. Why don't we just try to put a 2 right here? And then that gives me 6 bromine atoms, right? Or bromide ions. So I need to try to go make 6 bromides over here as well. So I put a 6 right there. And that throws off my hydrogens. I've got 2 hydrogens on the reactant side, but now I have 6 on the product side. So how can I make it 6 on both sides? Coefficient of 3 right here. So I'll go over the coefficients in black. We had a 2, we have a 3, we have a 6, and then there's an understood 1 in front of iron sulfate on the product side. Okay, you see how this is a lot of steps? This is a lot of simple things you've done in the past. Understanding charges on anions and cations, writing ionic compounds and formulas. But now we're putting it all together and we're writing multiple all in one reaction. And then I'm asking you to balance it on top of that. Okay? So if you recognize I am not where I need to be with cations and anions, don't be too prideful. Reach out to me. Let's set up a Zoom. Let's talk through some chapter 2 and 3 stuff. Let's get you where you need to be so that exam 2 doesn't literally destroy you. Okay. All right. Dicarbon tetrahydride. This is a different phrasing. If you watch the binary compounds video, you will recognize this. What I see when I read this is di and tetra. Okay, these were prefixes we had to use to denote how many of the following element is in my compound. So this is a covalently bonded compound, and this is how we name binary covalently bonded compound. So di is the prefix for 2, tetra was the prefix for 4. So this should be, we should have C2H4. This is a carbohydrate, and notice we're reacting with oxygen. Do I just write O? This is an element by itself, and this is a diatomic, so it's O2. So you have a carbohydrate and you have oxygen. What kind of reaction? Thank you, Lucy wrote it. This is combustion. So your product should be CO2 and H2O. Now, we got to balance this. You see now why combustion is my favorite? Because you really don't even have to do all the thinking about what the formulas are and blah, blah, blah. Let's balance this, but I encourage you to do oxygen last. Balance your carbon hydrogen first. So I got 2 carbons on my reactant side. I need 2 on the product side. So put a 2 there. Now I've got 2 carbons on reactant product side. And hydrogens, I got 4 hydrogens on my reactant side, so I need 4 on the product side. So now if I put a 2 in front of water, that also gives me 4. Okay, now add up the oxygens on the product side first because you have more oxygens on the product side. And then see what kind of coefficient you need to put in front of oxygen on the reactant side. So total, I've got 2 times 2. In one CO2 molecule, there's 2 oxygen atoms. But I've got 2 carbon dioxide molecules, so 2 times 2. I've got 4 oxygens here. That's not 4, it's 4 oxygens. Plus 2 more oxygens is 6 oxygens total. So I'm going to put a 3 right there. All right, we got 2 more to go, and we're kind of closing in on our time here. Wait, why did I write the product like that in the beginning? Wait, so what, Maddie?
So just like the CO2 plus H2O.
Why did I write CO2 and H2O?
Yeah.
That's always the products of a combustion reaction.
Okay, gotcha. I didn't write that down.
This one's why combustion's my favorite, because you don't even have to think about what products should you make. All right, calcium chloride and oxygen. Calcium chloride and oxygen. So I've got calcium is Ca, chloride is Cl. This is minus, and calcium is a +2. It's main group 2. So your formula for calcium chloride should be Ca, do the switch trick, CaCl2. And I'm not writing Cl2 because it's a diatomic. I happen to need 2 chloride anions to balance my calcium cation here. Calcium's not by itself. In this case, it is in the compound. All right, oxygen, we know from previous, our combustion reaction, oxygen is a diatomic. So I do need to write O2 there. So look at what reactants you have. I have a compound and a single element. So how could these things be rearranged? What does this look like from up here? I'll come back in just a second. We don't have 2 single elements, so it's not combination. We don't have a single element or compound. Cheated. We have a case of infidelity here. Single displacement. Now you got to ask yourself, what kind of single displacement? Is my lone element a metal or a non-metal? What is it going to displace? Is it going to displace the cation, the calcium? Is it going to displace the anion, the chloride? That's right, Keyshawn. This is a non-metal, so it's going to displace the chloride. So we've got to write a formula for calcium oxide. That's what we're going to make, Ca and O. We know oxygen has an anion. What kind of charge does oxygen have when it's an anion? Anion, there you go, -2. So you should have CaO. You just need 1 cation and 1 anion here, because calcium's a +2. That's right. That's right. That's what we wrote right up here. Metals displace cations and non-metals. I'm looking at why can't I get? I'm looking at this right here. I can never remember if it's Kiara or Kiara because I know I have both in the course. All right, and then plus Cl, and you do have to write it as a diatomic here, so Cl2. All right, and then is everything balanced? No, it's not balanced. So to balance it, we're going to need 2 oxygens on the product side. We got 2 oxygens on the reactant side. So what happened? There it is. 2 right there, which messes up my calciums. So I've got to go add a 2 over here in front of calcium chloride to give me 2 calciums on the reactant side. And now I need 4 chlorines or chlorines on the product side. I got 4 chlorides, so I need 4. So I'll put a 2 there. And I think everything's balanced after that. Okay, hang with me, we're almost done. I see the faces. Like, I'm tired of this. I know that face. Last one. Aluminum sulfide. Aluminum forms what kind of cation? Cation with a what charge? +3. Thank you, Summer. So it should be Al. This is going to be a +3. Sulfur is S, but it's going to be a -2. So do the switch trick. How many of each do I need? What subscripts do I need in this formula? I'm going to need 2 aluminums, 3 sulfides. And this is all we have. So do we even have a reaction? What's happening here? Here's what I see. I see 2 elements happily married. Well, maybe not happily. They're married. Okay. Haley said it. This is going to decompose. Heartbreak. All right, A-L, and then S. And we can just write these. Neither of these are tragic, I know. Neither of these are diatomics, okay? So now we just balance it with coefficients on this side, 2 and 3. Okay, I am very interested to know how you guys feel about all this. So in my last 3 minutes, I'm going to ask you a poll question that I've asked you before. Be brutally honest with me. How much of this sunk in today? I do have some more slides while y'all are answering that. We didn't get to, just some more practice. I encourage you to take a look at those things. I am going to open up the Mastering Chemistry homework for Chapter 5 today. So now that we've started Chapter 5. And that'll be due a week from tomorrow on the 12th. So 12th of March. And anyways. All right, we're 96% voted in the polls. Wow, this is what I feared. We get a good distribution here. A lot of people said they got a lot of it, but also a lot of people said maybe half or less. So maybe you just need some time to process it and re-go over your notes, and that's fine. But if you need to reach out to me, please, please, I cannot ask you enough. Set up a Zoom. I had nobody come to my office hours today. But remember, I'm always available via the Zoom links on the syllabus for office hours, Tuesdays and Thursdays at 9:30 to 10:30, and Friday, so tomorrow from 12:30 to 1:30. I'm just gonna be sitting in front of my computer, okay? So please drop in, and I'm happy to talk through anything that is just overwhelming to you, confusing to you, whatever it may be, okay? There's no dumb questions, so. All right, well, that is all I had for today, so I hope you guys have a great weekend. And if there's any questions right now, I'll hang out for a minute. But if not, I'll see you guys in labs whenever you have your lab.